to our next session, we have with us Dr. Manju Henry from Rutherford Appleton Laboratory, UK. It's an honor for us to welcome her, who's also an alumni of Department of Electronics. The title of the talk is the Hyperspectral Microwave Sounder Constellation of Nanosatellites for Climate Change and Mitigation. We welcome you, ma'am. I now welcome the distinguished chair of the session, Professor Katie Matthew from CUSAT. I would like to hand over the platform to the chair.
Thank you. Dr. Manju, as an alumni of this great institution, I am very happy to invite you to this webinar, APSYM 2020.
Yeah, I'm pleased to come and give a talk to the university
nice.
as well.
It's my pleasure.
Yeah, it's
yes.
And thank you very much for the introduction as well. So
okay.
I will start presenting my.
No. Let me introduce you.
Yeah. Okay.
Okay. It is my pleasure to introduce Dr. Manju to you. Dr. Manju Henry is currently working as the section leader of a millimeter wave technology group for small satellite payloads at RIL Space Science and Technology Facility Council, UK. She obtained her PhD degree in electronic engineering from CUSAT in 2002 and completed 5 years of postdoctoral studies at the Karlsruhe Institute of Technology, Germany and University of Surrey, UK. She is a leading technologist in the development of terahertz instrumentation, developed devices and systems for use in Earth observation and astronomy and material processing. She has undertaken key roles in several European Union, European Space Agency, European Southern Observatory projects, including Atacama Large Millimeter Array Telescope, METOP second generation satellite. Please, Manju.
Yeah, thank you. Thank you very much for your introduction. Yeah, I'm going to talk about the millimeter wave, submillimeter wave sensing from space. We look at a case study. It's a hyperspectral microwave sounder constellation of nanosatellite for climate change and mitigation. I'm working in the millimeter wave technology group at RAL Space STFC. So, give you an overview. I will give an introduction. I will explain the teraheads science application and its impact. Give some examples on teraheads astronomy missions from space, like Herschel, HIFI, and Planck. And we'll look into the Earth observation mission examples like METOP second generation. And the next generation meteorological sounders, which is the main topic of my presentation, that's a hyperspectral microwave sounders, and look into the case study of HYMS constellation of nanosatellite for climate change and mitigation. So give an introduction on RAL Space and Millimeter Wave Technology Group before I go into the technical presentation. On the right-hand side is the aerial view of RAL Space at the Rutherford Appleton Laboratory, which is located 30 kilometers south of Oxford in UK. RAL Space is an integral part of Science and Technology Facilities Council, which is one of the research councils in UK. In addition to STFC, along with 6 other research councils and Research England and Innovate UK constitute the UK Research and Innovation. So basically, I'm part of RAL Space, STFC, UKRI. RAL Space is involved in the world-class science research and technology development, and we have been developing space programs, experience and expertise involved in more than 210 spacecraft missions so far. We work throughout the life cycle of the space missions. So starting from the inception of the design, the conceptual design of the future mission, defining the requirements, and then involved in the design of technology and also scientific instrumentation, then handling of the data, and also in the providing the test facilities. For example, we have the vibration facility, we have the space test chambers for testing satellites, for testing instruments, as well as components. So another test facility is also being developed on campus. It's called the National Satellite Test Facility, which will have an 8-meter vacuum chamber, which will replicate the space on Earth, on ground. And we can do testing of the satellites ranging from very large satellites to small satellites in this facility, which is going to be commenced in 2022. So coming to millimeter wave technology group, we are developing cutting edge technology for frequencies ranging from 20 gigahertz and going up to 2 terahertz. So we start from the scratch, designing the devices. That's like the critical components like Schottky diodes. We manufacture and design it in-house. Then we are involved in the component development and design. For example, starting from free space components like frequency selective surfaces, antennas, mirrors, going into passive components like diplexers, orthomode transducers, and active components like mixers, multipliers, etc. Then we build the system, and mainly the systems for radio astronomy and Earth observation. So millimeter wave, submillimeter wave, if you talk about this frequency range, it lies in between the microwave and the infrared. In terms of frequency, is 30 gigahertz from up to 3 terahertz. 1 terahertz is 1000 gigahertz. So this frequency range compared to gamma rays and X-rays, they have very low power. So the photon energy is quite small. So I'm calling them not in terms of wavelength, but in terms of energy. They are small waves, but they have huge impact. So millimeter wave, submillimeter wave, what are the unique attributes? They are, as I explained, they have very low energy. Low energy implies non-ionizing, and they are considered safe for human exposure compared to X-rays and gamma rays. They are able to penetrate through clothing and various dielectric materials that are opaque to visible and infrared. Because of this reason, we can use terahertz in passive screening for security screening in airports. So you can see the photograph of a passive scanner used in an airport for looking at the concealed weapons. You can also look at the chemical molecular species of water vapor, oxygen, carbon monoxide. You can measure all this. And because of the bandwidth this frequency range is offering, you can also have application in ultra high data rate communication. But the most important application and having science impact, which I explain in my next slides. So if you look into the universe with different types of terahertz signals or with EM waves, visible light or X-rays or gamma rays, you see different physical objects. For example, if you are looking with X-rays or gamma rays, you can see active galaxies. If you look with visible light, you can see these light coming from the stars. Instead of that, if you are using terahertz and millimeter waves, submillimeter waves, the benefit is you will be able to look into the cold, dark, interstellar medium and cosmic microwave background. Using this, you will be able to understand the stellar and galactic formation and evolution of the universe. Similarly, this can be the terahertz radiation can be used for studying planetary atmospheres like gas giants and comets, and it also gives you information on the solar system. in order to get the best resolution, you have to do in situ or close encounter measurements, but there are no teraheads landers yet. Similarly, coming to the Earth observation, if you can study the oxygen and water vapor in the Earth's atmosphere, in the upper and lower atmosphere, you can do the weather forecasting and also numerical weather prediction. So, astronomy observations. So when it comes to astronomical observations, we have heard about a lot of ground-based observatories like Mauna Kea in Hawaii, the Stewart Observatory in Arizona, the Atacama Large Millimeter Observatory telescope in Chile, in Chanjandor Plateau. All these are constructed in dry areas at very high altitudes. This is because there is atmospheric absorption when there is water vapor. So to reduce this atmospheric absorption and to detect these faint signals, usually they are located at high altitude. Even at these excellent sites, atmospheric transmission is quite limited. This is shown by the photograph on the right-hand side. If you look at the transmission from various sites, including from Ridge A on Stewart Observatory and Mauna Kea and Chanjandor, you can see the transmission is significantly falls down because of the absorption in the atmosphere. So higher altitude observation is the best. So we can reduce this atmospheric absorption. An example is SOFIA. We can do this observation from airborne observatories. An example is SOFIA Observatory. But the conditions are still not perfect. If you look at the red and the black curve, the red curve is from the good ground side and the black is from the SOFIA Observatory. So for astronomy, the best situation is no atmospheric attenuation, gives you perfect seeing conditions. So this can be tolerated, but it's still not good. So the best is the space. In the space, there are three classes of orbit. If you look into, there is low Earth orbit. That's where most of the weather satellites are launched. You have medium Earth orbit. They are used for navigation and specialty satellites. And the communication satellite from the geostationary orbit. As we go high in orbit, the time it takes for the rotation increases. So for example, if you are observing from, for example, 700 kilometers, the time it takes for one rotation will be around 99 minutes. From 3,600 kilometers, it's around 23 hours and 54 minutes. So in the geostationary orbit, you will be looking at the same point on the Earth always. Another sweet orbit is these Lagrangian points. So the benefit of Lagrangian points is that the gravitational pull from the Earth will be cancelled by the gravitational pull from the Sun. So there will be, these are stable orbits. So we have several Lagrange points, L1, L2, L3, L4, and L5. These are done for solar observations and studies. Beyond that, it's used for planetary exploration. So space is the best for these scientific observations and studies. Give you an example of a space mission. That's the HIFI, Herschel HIFI, which is launched by ESA. So one of the instruments used on this is the Heterodyne instrument for far infrared. This was used for studying the evolution of galaxies, star and planet formation. The payload is located in this case at the focal plane of the 3.5 meter diameter telescope, and it has very sensitive receivers. These receivers are superconducting insulated superconducting receivers operating in the frequency range from 0.5 terahertz going up to 1.9 terahertz. These receivers requires cooling, so they are liquid helium is used as the coolant. But the problem is it will stop functioning properly when it ran out of the coolant. It has achieved a lifetime of 3 years from Lagrange point 2 location. And the spectral resolution achieved was 0.1 to 1 megahertz. Another example is used in teraheads astronomy application is the Planck Cosmic Microwave Background Observatory. So cosmic microwave background is the leftover radiation from Big Bang. Over the billions of years, the universe has been expanding and it's cooling greatly. Due to the expansion of the space, the wavelengths of the photons are increasing because there is a redshift. Currently, they are in the frequency around 1 millimeter to 2 millimeter. So the frequency range from 150 to 300 gigahertz. And the temperature is around 2.7 Kelvin. So it's ideal for studying. The millimeter wave observations are ideal. Sub-millimeter wave observations are ideal for studying this CMP observatory. In Planck, there is the low frequency instrument with instruments ranging from 30 gigahertz to 75 gigahertz. And here the instrument is cooled to 20 Kelvin. And for the high frequency instruments ranging from 0.1 terahertz to 0.9 terahertz, it's cooled to 0.1 Kelvin. Now coming to Earth observation from space. You can view Earth atmospheric species that are not visible from the ground, from the Earth's atmosphere. Doing so, you can see through aerosols. If you consider visible and infrared, they won't be able to see through the aerosols, but in the case of the microwave, you will be able to. I have a small video showing how these polar satellites are orbiting around Earth, and the Earth is rotating as well. Because of this reason, we will get a full global coverage. So these meteorological satellites, like METOP second generation satellites, will be able to measure the water and oxygen in the Earth's atmosphere and thereby predict the precipitation and atmospheric temperature. And the polar orbits provides full global coverage, as you have seen. So why millimeter waves? If you think of infrared, there are different types of instruments available for weather forecasting. This will include infrared, there are microwave sounders, infrared imagers are available. There are radio occultation instruments, but out of all these, millimeter waves have the most significant impact because they allow the global observation of temperature and weather in all weather conditions because they can penetrate through cloud. If you look into the Earth's atmosphere, you can see that if you look at the NOVA satellite view of Europe, it's covered with cloud. If you consider most of the time, any point on the Earth or the Earth's surface is covered with 50% with cloud. So most of the events happen in the order of hours when it comes to severe weather events like hurricanes or tornadoes. They are usually cloud shrouded and the key observables vary within 15 kilometers and 15 minutes. So you need to make very frequent observation. At the same time, you have to use instruments with millimeter waves, which reduces the forecast errors significantly. So these millimeter wave instruments play a crucial role in weather forecasting. So one of the examples of Earth observation mission is the METOP second generation. These satellites are currently being built. This is going to be launched in 2022 and will be operational until 2040. Each launch will contain 2 satellites, A and B, and there are 3 pairs. They will be launched into 800 kilometers and their lifetime is around 7 years. So you get a total of 20 years coverage and the observation will allow you to go beyond 2040. So the satellite instruments will be able to provide temperature, humidity, wind speed, trace gases, land and ocean images. There are 3 instruments on board METOP second generation satellites, which are millimeter wave, operating in the millimeter wave, sub-millimeter wave range, going up to 600 gigahertz. They are microwave sounders, microwave imagers, and ice cloud imagers. So we have been at Millimeter Technology Group was involved in the development of the receivers for the METOP second generation satellites. For all these instruments, microwave sounder, microwave imager, and ice cloud imager. Above 100 gigahertz, we are using heterodyne systems. What's the heterodyne systems mean? The feeble signals from the Earth's atmosphere is collected by the antenna, as shown in the figure. It's amplified by a low noise amplifier. It will add less noise into the system. And we have a mixer for down converting into intermediate frequency. This is done by mixing the incoming signal with the local oscillator signal, and a difference in the frequency is generated, which is called the intermediate frequency. Intermediate frequency will be at lower frequency. So there are components available for processing these intermediate frequency signals. Either we can use filter banks or use back-end spectrometers for processing the spectrum. For this, we are using a lot of components developed in-house. For example, we have packaged these low noise amplifiers, we have mixers, multipliers, and as well as space qualified Schottky diodes to build these instruments. So here are some photographs showing the engineering qualification model of the front-end receiver we developed for microwave sounder instrument at 229 gigahertz. So also for the microwave imager, two receivers, one operating at 166 gigahertz and 183 gigahertz. You can see here the RF modules, the LNA, and at the input port, the antenna will be connected, and you can see the mixer. The local oscillator signals coming in will mixed and down converted into intermediate frequency. For these, most of these components need DC, and there is a DC electronics box which is used for supplying the bias for the various components in the instrument. So we have successfully done the flight testing, and 160 gigahertz flight model has been shipped last week to APSYM for integration. So another important work we are doing is the calibration. We need to calibrate these instruments on ground before launch. An example on MWS, microwave sounding instrument, is a Crosstrack Scanner. So when the satellite is flying, you can see the scanner. A nonlinear scanner will be doing the scanning the Earth. At the same time, it will be looking into the cold space as well as into the onboard calibration target. So why we need a calibration target? The calibration target and this cold space view are required for calibrating this instrument. So the calibration targets usually have absorption very high. So whatever signals falling on it will be absorbed. Therefore, the emissivity is equal to 1. So why we need that high absorption is if the emissivity is equal to 1, you can say the physical temperature measured is equal to the brightness temperature. Brightness temperature is the unit we measure the radiance from the microwaves, radiance going from Earth's atmosphere into the satellites. So the fabrication was quite challenging, and also the design is quite challenging here. It consists of aluminum pyramids, which is coated with ecosob material, which is carbon with iron loaded material. We can't use very thick, like thick layers of absorbers cannot be used because that will increase the variation of temperature between the pyramid tip and the base. In the base, we have thermometers for measuring the actual physical temperature of the target. So before launching, we test it in our thermal vacuum chambers, replicating the space environment. So we have the two calibration targets. One calibration target is maintained at 80K, and the other one, the temperature is varied from 80K to 315K, and that will replicate an Earth target. So you can see here we have measured a return loss less than minus 45 dB over the entire frequency range where the instrument is operating from 20 gigahertz to 230 gigahertz. So we have a major challenge in terms of climate. Extreme events are on a rise. The catastrophes resulting due to these extreme events are causing billions of losses. If you compare to 1980 and to 2018, almost these number of natural loss events almost doubled. So these are from various like geophysical events, meteorological events, hydrological events, and climatological events. So this is due to global warming. The average global temperature is rising, and this is leading to acute hazards such as heat waves and floods. They grow in frequency and severity, and chronic hazards such as drought and rising sea levels are also intensifying. So what we need is an improved weather forecasting. So that's what I'm looking for into hyperspectral microwave sounder. So the Earth observation have current meteorological satellites, which we are being built and going to be launched, have serious limitations. Let's look into what are the problems with the current meteorological state-of-the-art meteorological satellites. They are large satellites and they need a capital commitment over 300 million pounds. And because it's being developed on large satellites, so costly, frequent technological updates are not possible. And the number of satellites you can launch in the orbit is limited to 2. Take the case of METOP second generation. You will have 2 satellites in operation, which will give you a revisit rate of 12 hours. What I mean by revisit rate is the number of times the same satellite see the same point on the Earth. When it comes to hurricanes, as well as the transient events like tornadoes, in these cases, we have to increase the revisit rate at least to 30 minutes. So this is a serious limitation of our weather satellites. And another important limitation is they are giving low resolution because the spectral resolution is quite limited. And this reduces the accuracy of weather forecasting. With the rollout of 5G is going to be a serious threat in the future for our weather satellite. This is because these interference signals will mask these faint signals coming from the Earth's atmosphere. So that's also going to be a serious threat. How we can address this problem? That's why we need these hyperspectral microwave sounders. What's a hyperspectral microwave sounder? We have 2 channels in this HYMS instrument. One operating from 50 to 68 gigahertz, that's for oxygen sensing and temperature profiling. 175 to 192 gigahertz channel, and that's for water vapor sensing. This is first of its kind. This hasn't been demonstrated before. Hyperspectral microwave sounders improve the spectral resolution by 100-fold. So as a result, the accuracy of weather forecasting improves. So this is what's a HYMS constellation of satellites for climate change and mitigation we have proposed. So this gives a rapid revisit rate of better than 30 minutes if you can launch a constellation of nanosatellite, which will be cheaper compared to these large satellites. And this will also give a better spectral resolution. So let's look into compare these 2 cases with METOP second generation and the hyperspectral microwave sounder. On the METOP SG, you're looking at the a mass or a weight of around 4,000 kilos. Whereas for the hyperspectral microwave sounders, you are looking into 20 kilo. The number of channels in this case is increased to 1,000. Whereas in the METOP second generation satellite instruments, the maximum number of channels is 20. So with hyperspectral microwave sounders, think about these spectral channels give you different slices from the Earth's atmosphere. By increasing the spectral resolution, you will get more information from the Earth's atmosphere, which will improve the accuracy of weather forecasting. So we are expecting an improvement of 30% in precipitation and 10% in temperature observation. By this will increase the vertical resolution and thereby improves the vertical forecast accuracy. And it's also crucial for noise mitigation, because in the future, as I explained, it's going to be a major challenge for the weather satellites because of these interfering signals. So the benefit of hyperspectral microwave sounders, because they have numerous channels, if there are interfering channels, it can be removed without loss of information. So that's the benefit of hyperspectral microwave sounding. We have done the technology development of this instrument. The requirement was, it was quite technically challenging, the development was. The reason being, the radiometric precision or the sensitivity required was 4-fold better than the current instrument being developed for METOP second generation. We have managed to achieve this using very low noise amplifiers and also using ultra high resolution spectrometer as the backend. We measured a system noise temperature less than 200 Kelvin. That means we are getting an NE delta T. That's the minimum noise temperature measured of the order of 0.25 Kelvin. So there is some margin there as well. And the wideband spectrometer was developed by Star Dundee. It's a company that's spin out from Dundee University. And they have developed the spectrometer and a factor of improvement of 40 compared to the baseline. So one another challenge is miniaturizing the radiometers, because these radiometers we can't get it installed on nanosatellites. If we can't miniaturize the hyperspectral microwave sounders, then we have to go for large platforms. Then it will be difficult to launch a constellation, which we are planning of 30 satellites to get the 30-minute revisit rate. So we managed to get all these components packed by putting it into vertical stacks, and an ultra compact radiometer was built and tested, and it gives similar sensitivity to the better than the microwave sound radiometers. The volume is reduced by a factor of 50. So you can see here the electronics, the DC, you have seen earlier, all these coaxial cables are replaced by flexible PCBs, and all the waveguides are integrated inside this module. So you have all the functionalities inside this small block, including low noise amplifiers, mixers, multipliers, everything are integrated into the block. You also have the compact wideband spectrometer reduced into a size of 100 by 100 by 46. So we can accommodate the whole radiometer inside a nanosatellite. So this is the roadmap we are planning. So initially we demonstrated the instrument in the lab. The next step is to take it into an airborne demonstrator. So we usually measure it on facility for airborne and atmospheric measurement. It's a NERC facility, Natural Environment Research Council facility. So we are going to test the instrument in January 2021. Then we also got the funding to develop a pre-prototype payload for a nanosatellite. And we are hoping that we will be able to launch it by 2022. And a constellation can be built by 2027. We are looking for funding from private and government grants to realize our ambition. So why now? So new space is opening up because the launch costs and the spacecraft costs are rapidly decreasing. The weather previously was part of meteorological institutes, but now even NOAA, the US Meteorological Institute, they are considering incorporating private weather data. So it's a rapidly emerging market. There is huge processing power available. So there is advances in computing and AI, and this will help us to give actionable insights into the weather. And we also will be able to address the congestion of frequencies using hyperspectral microwave sounders. So it's a favorable economics and emerging market opportunity. So these are very important for addressing science and also real world challenges. An example, I have shown a couple of examples for the explaining the global impact. For example, the Event Horizon Telescope. Event Horizon Telescope is a collection of telescopes that's all over the world, which work in unison to take the photograph of the black hole shadow. And they managed to take with the millimeter waves using ALMA telescope and the JCMT telescope at Hawaii. They managed to take the black hole shadow of the M87 galaxy, which is a significant achievement. If we can build this constellation of hyperspectral microwave satellites, we will be able to mitigate against catastrophes like hurricanes and tornadoes. It's also quite crucial for managing future energy resources, because these energy resources like wind and solar is dependent on weather. So it will help to manage the grid and also managing the managing our energy resources. And also this HYMS and Spectre constellation is that Spectre is another instrument I'm building for frequency monitoring as well, which is crucial for future 5G threat for our weather satellites. So I'm concluding my presentation. So we have looked into the benefits of teraheads, what's its importance to Earth observation and astronomy. This provides key astrophysical information relating to stellar and galactic evolution. It's also very important for remote sounding the Earth's atmosphere. Teraheads observation from space will increase with METOP-SG and small generation of constellation satellites we are planning. There are also other wider operational benefits like weather prediction, security, transportation, gas sensing, telecommunications, etc. These wave energies are quite small for these teraheads, but they have huge impact. And thank you very much for listening. The new innovations will lead to new space, and it's open for questions.
Thank you, Manju. Now it's time for interaction. You can ask questions.
Hello.
Hello.
Yes.
I would like to know that how is 5G going to affect your weather satellite to such a great extent?
Yeah.
And
so
5G is a fully planned activity for this. And then if 5G is going to bother, then 6G may bother you more. So
of course,
what is the mitigating things which we are thinking of?
yeah. So the 5G currently it's up to 24 gigahertz. The meteorologists are really worried because even the harmonics can cause interference. An example is the small satellite SMOS, and that satellite with the it's operating in the 1.4 gigahertz. The effects of RFIs on this small satellite is significant. Yeah. So yeah, so we are expecting that if it rolls into this frequency range, it's going to affect our weather satellite. So only option is to have instruments which are resilient to 5G. HYMS is an example. So everyone is planning, even NOVA is thinking of all the future instruments need to be hyperspectral. So the benefit is even if you are contaminating your channels, some of these channels, we will be able to remove these channels without loss of information. Whereas in the current satellites, where the instruments have limited number of channels, even if you lose 1 or 2 channels, you will lose a lot of information.
So, thank you very much. It's a very great research work which needs to be done. And then, of course, we have other bands of IR, VNIR, etc. But they are all not microwave based. They are, of course, they are based because of the problems of actual detection. And then this one, I mean, they have limited applications. So anyway, this microwave sounder and this will have a great application in future. And I think, or possibly they have to look for real bands where they could exclusively operate. I think that is also another thing which they have to see.
Yeah, there are protection provided by these, like ITUs, they provide protection. But the problem is the protected channels will be okay. But in the nearby channels, where there's the harmonics the window channels will get affected. So for example, if you take 5G, it's going up to 24 gigahertz at the moment. If you take its second harmonic, it's in the 50 gigahertz, in the oxygen band.
In that oxygen band, correct.
So that's going to be a problem in the future. We know the might of the telecommunication. They won't stop. They will get extended to higher frequencies. So we have to take our own measures to be resilient to the RFIs.
Communication anyway is a must and has to take top priority. Otherwise, we can't even talk to each other. Thank you very much.
Thank you.
Dr. Manju, your work is very challenging because your scanning passive radiometer is operating with a frequency range of 23 to 229 gigahertz, and also the temperature variation is from 80K to 350K. It's very challenging one, no?
Yeah, it is. It's quite challenging, and developing this instrumentation, because it's basically at higher frequency. When you go higher in frequency, all the sizes will come down. So if you're manufacturing the waveguides, the size goes significantly small. So we have this very high like precision development facility where we manufacture, we have these kern machines and nano machines, which enable us to achieve these waveguide sizes. So it's really challenging.
Any questions, please?
Hello.
Yeah.
Is 5G safe for human health?
I don't think it will be an issue because that's what I explained previously. We have seen that they are non-ionizing. Compared to X-rays and gamma rays, these microwaves and millimeter waves, they are very less power. So there is not much research done in this area to prove that they are going to affect your health. So I don't think it's going to be a problem. It's something like people are exaggerating on it.
Okay, one small question out of curiosity. After your course in QSET, which other course led you to reach this point?
Okay, so I have, after completing in 2002, I worked as a postdoctoral researcher at Karlsruhe Institute of Technology in Germany for 2 years. Then I worked in 3 years at University of Surrey. Then I moved to STFC, Rutherford Appleton Laboratory in 2007. So I have been working in the lab for the last 13 years now.
So as a doctorate, you left QSET, isn't it?
Yeah, I got my PhD from
who was your
University.
guide?
as Dr. C.K. Anandan.
Oh, very nice. Very happy. Very proud. Okay, nice. Nice.
Any more questions?
Hi, Manju.
Hi, Anandan sir.
Nice to see you presenting.
Yeah, thank you.
Okay, thank
Then,
you. Yeah.
okay, let me conclude then.
Thank you.
Dr. Manju, your
Excuse me.
research field is very interesting and relevant, mainly for weather forecast, atmospheric study, global warming, etc. You have presented the work very beautifully with enough supporting data. It is rather an exhaustive study, including the challenges and the limitations. I am very happy to see that you have filed for patent also. Congratulations.
Thank you. Thank you.
Excuse